Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. This is lecture number 53. Now, before we proceed to today's content, I want you to make note of one thing from the previous lecture. That is lecture 52 and tutorial 14, I believe. Okay, it is that. And now I want to correct some mistake I made. So please note this correction. So in tutorial 14, that is lecture 52, I had written that my N2 by N1, this is based on the Boltzmann distribution, right? I had written that is given by G2 by G1, where G2 is the degeneracy of the second level and G1 is the degeneracy of the first level, times e to the power minus beta delta E, right? So now I had by mistake, the mistake I made was defining my delta E to be E1 minus E2. The correction should be that delta E should be E2 minus E1. The reason is very simple, because we had obtained this as nothing but G2 by G1 times e to the power minus beta E2 divided by e to the power minus beta E1. All right. So now if you take a look at this equation, right? Now while this beta E1 goes up, right, it becomes positive, but there's already a negative sign here. So in the last tutorial, I had missed this negative sign. So then we realized that, oh, this is a mistake. So I immediately corrected in this lecture. So please note this, okay, right? So this was the mistake made in the 14th tutorial and lecture 52. The correction has been provided right here. All right. So please note this simple, like arithmetic mistake, but it's an important mistake nonetheless, but which has been corrected. Now, as I made this correction, I wanted to tell you about a clarification from, I think lecture 43 it was, okay, right? I wanted to tell you in the tutorial, but we did not have the time, so I'll address this today. It is that a clarification from lecture 43. Now you may be wondering, oh, what is this person doing? From lecture 53, I ask you to go back to 43. Especially if you're seeing this online, you can always go back to lecture 43, or you can take your notes and then look at lecture 43. Okay. Now I want to tell you that there was one particular stage where we used the expression N2 by N1 is equal to G2 by G1 times e to the power h nu by kBt. Recall, right? Now, note that in lecture 43, I first wrote minus h nu by kBt, right? And then corrected it as h nu divided by kBt. Now, where is this coming from? Where is this positive sign coming from? Now, this positive sign is coming from the fact that my delta E is equal to E1 minus E2, which is equal to h nu. All right. So which is equal to minus h nu. Okay. Because it's E2 minus E1, that gives me like plus h nu. But recall that from this expression right here, there is already a negative sign, right? So my beta is equal to 1 over kBt. Okay, so that is why you get this 1 over kBt term right here. Okay, right? So and because there is this delta E is in that particular lecture was defined as E1 minus E2. In fact, I did not even define delta E at all. I wanted to tell this clarification in the previous tutorial itself, but there was no time, so I'm telling it now. All right. So please be clear as to why I used e to the power h nu over kBt in lecture 43. Okay, right? So now we're able to put together everything. That is, any expression related to the Boltzmann distribution that we use, we saw how it is obtained, right? And how it is all coming together in the context of astrochemistry, because we use this equation while deriving the connection between the Einstein coefficients. Okay, so please note this. All right, and because this delta is E1 minus E2, which is equal to negative h nu, and because this expression already had a negative from this sign, right? From this part right here, it is coming from the negative beta. So therefore, overall, this becomes plus h nu by kBt. And then when we took the reciprocal of this, we got n1 by n2 is g1 by g2, and then this became e to the power minus h nu by kBt. Are we good, right? So this was a clarification I wanted to make. Okay. So in this lecture, so what we've started with is, I started off by correcting a mistake I made towards the end of the last lecture. That is in lecture 52, that my delta E here, right, by mistake, I had said that it was E1 minus E2. No, that is not correct, because obviously while this is going up, right, it should be positive, but there is already a negative side here. So this should be E2 minus E1. That's the correction. And once that, the Boltzmann distribution has been derived, I can now tell you as to why I made this change in the middle of the class in lecture number 43, right? And how I could get away with it. I could get away with it because, fortunately for me, right, in the class itself, I did not define what delta E was. Okay, but now I could clearly explain what was done. Okay. On that note, we shall proceed towards today's lecture. Now, we have been looking at a lot of things related to astrochemistry, right? So in some ways, right, it's kind of helpful to just tell you a brief summary as to what exactly we are doing in this course currently. Okay, right? So note that we are in the phase of detection of molecules. Like, you can call this where are we in this course? Okay, right? So as part of detection of molecules, right, we had to first see, about absorption and emission spectroscopy, right? That's what we saw, when probably, I don't know, some 20 or 30 lectures earlier, when we saw that using the Fraunhofer lines, we could measure, we could identify that, the same elements that are present on Earth are also present in the sun. Okay, right? So we started off with this, and after this, we said that this is for atoms, right? And then for molecules, we had to first understand the different types of motion, that is rotation, vibration, and electronic motion, right? And then, like, I had to inform you that to detect molecules in space, we needed to understand the interaction of light with matter, right? And so as part of it, we understood that light and matter, they both exhibited wave particle duality, which meant that we had to study them via the tools of what is called as quantum mechanics, correct? And next, we were discussing, we discussed some elementary aspects of quantum mechanics, some very basic aspects of quantum mechanics, right? We looked into that, and after that, what we did was, I also, then we started studying the interaction of light with matter, right? In that sense, we started studying about the Einstein coefficients, and how they were related. And then in some tutorials, right? In some tutorials, we understood while discussing the Einstein coefficients that this concept of a local thermal equilibrium kept coming again and again. So in the tutorials, we understood what local thermal equilibrium meant, and also derived the Boltzmann distribution. But don't forget this aspect that this is all fundamental physics and chemistry, and so much of fundamental physics and chemistry goes into detection of molecules in space. Okay, right? So what looked like a detour into like deep realms of physics and chemistry is absolutely essential, so that you understand all the techniques that are used to detect molecules in space, which is a non-trivial task, right? And look at the amount of fundamental science that goes into this applied interdisciplinary area of astrochemistry. Okay, now in the next few lectures, I'll write on here, in the next few lectures, we shall be looking at some more aspects of atomic, molecular, and electronic spectroscopy, right? Electronic spectroscopy as relevant for astrochemistry. Okay, so this is where we are. So I give you this summary because it is very easy to get lost in the details as to, oh, so much of physics and chemistry, but what is the connection with astrochemistry? All right. So never forget the connection with astrochemistry. It's always there. All right. So that said, I shall now begin with some aspects of atomic spectroscopy in this lecture. So atomic spectroscopy for astrochemistry. All right. So this is what we shall be looking into now. Now, recall that as part of atomic spectroscopy, we already started, this lecture, several lectures ago. Okay. For example, while we were discussing the topic on absorption and emission, right? Even then, therein itself, we were discussing a lot of aspects of atomic spectroscopy. We shall continue with that. Okay. Now, before we proceed further, a quick question. What do you think is the most abundant element in the universe? Well, the answer is straightforward. It is hydrogen, of course, right? It is hydrogen. So the spectroscopy of hydrogen atom itself, okay, right? H atom spectroscopy has played a major role in astronomy and astrophysics, okay? Major role in astral sciences, I'll put it this way, in the astro sciences. Okay, right? Now, in fact, hydrogen atom spectroscopy is also what was in one way, right, a precursor to the field of quantum mechanics. You may have studied in your 11th and 12th standard, right, in physics and chemistry, how the hydrogen atom spectrum resulted in a problem that was first, kind of empirically solved by Bohr, making some approximations, some very clever and smart approximations, which rather turned out to be, of the same results obtained by a much broader field called as quantum mechanics. right? You recall from your 11th and 12th standard? So hydrogen atom spectrum is extremely important because it is, after all, the most abundant element in the universe, as we saw in probably the second or third lecture of this course itself. Okay, H atom is most abundant in the universe. Okay. Now, when you actually talk about hydrogen atom spectrum, right? Especially the lights that are coming from various interstellar sources, because H atom is dominant there. A lot of interstellar sources, they emit lines which correspond to various atomic emissions and absorptions from the H atom. Okay, in particular, right? So H atom, right? There are a few prominent lines. Okay, few prominent lines which are called as H alpha, which occurs at, I think, around 656.3 nanometers. H beta, which occurs at, if I'm correct, 486 nanometers. And then your H gamma, which occurs at 434 nanometers. And H delta, which occurs at 410 nanometers. These are very prominent lines. Okay, I hope by now I don't need to explain why these lines come up, right? Because we spent at least 2 or 3 lectures explaining what a spectral line is, what causes it, etc., right? We had to undergo so much of training in all these aspects. So now we can use the language and jargon pretty readily. So these prominent lines are often seen in the spectra of interstellar objects. Prominent lines from space. I'm just calling space as the interstellar medium, very vaguely. So in a lot of sources, these 4 lines are seen. Okay, I will delete this part now. It was subsequently found out, okay, right, that these 4 lines, by around let's say 1900 or close to sometime around that, okay, right, it was found that these particular lines, okay, these predominant lines, the H alpha, H beta, H delta lines, okay, right, that these 4 lines, H alpha, H beta, H gamma, and H delta lines, right, they correspond to hydrogen atom undergoing transition from n equals 2, right, n equals 2 to various upper excited state levels. Upper excited state levels. Now please note this. What have I written here? I've written here that it corresponds from the n equals 2. What am I talking about when I say n equals 2? Any idea? I'll delete this part. I'll retain the bottom part though. So this is going to be page number 8. So what do I mean, when I say that n equals 2 for the hydrogen atom? Is you correct? By n equals 2, I'm talking about the principal quantum number. The principal quantum number. Recall that each atom, right? Each atom is associated with 4 quantum numbers, right? Remember from your elementary general chemistry or physics, modern physics courses, N, L, M sub L, and S. Now these 3 wave functions correspond to the spatial part. They come from the solution of the Schrodinger equation to the hydrogen atom, and this comes on its own. I mean, you can either introduce it in an ad hoc way, or you get it from what is called as the Dirac's equation. But that besides. So each atom has like 4 quantum numbers. From that, the n quantum number corresponds to the principal quantum number. Now, what is the least value of the principal quantum number for the hydrogen atom? N can be what? N right? N can be what? N can be 1, 2, 3, blah, 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 right? So it begins from 1. Now, what is the beauty here? The beauty is that, right, in a lot of spectra that you get from the interstellar medium, right, the emission, the H alpha, H beta, H gamma, and H delta, they correspond to n equals 2 and not n equals 1. Okay, right? I'll also put it. And not n equals 1. What does this tell you? Now, what is the difference between n equals 2 and n equals 1 level? It is the second excited state, right? I want to avoid the use of the phrases orbits, orbitals and all, okay? Because, quantum mechanically they are an incorrect description. I will just tell that it corresponds to the second excited state, right? It does not correspond to the ground state, but it corresponds to the second excited state, okay, right? What does this tell? It tells us that, right, the fact that these emissions correspond to the n equals to 2 level tells that the temperature of several of these sources from, let's say, outer space is high enough to provide the energy. Otherwise, why should the emission occur from n equals 2 state, right? Is high enough to provide excitation energy. Excitation So in case you don't understand my handwriting, I'll tell you clearly that the fact that, okay, right, these lines correspond to the n equals 2 emission, right? The starting point as n equals 2 emission tells us that, in several of these sources, right, the temperature is high enough to already excite the electron from the ground state to the n equals 2 state. All right. Of course, there is also going to be some emission from n equal to 1, but the predominant mode of emission is going to be from n equals 2. So therefore, by studying, okay, right, by studying these series of lines, so the point is that by studying, okay, right, by studying this H atom lines, we get to understand about the temperature, okay, right? We get to understand about the temperature of the source, right, that is emitting these lights, that is emitting these spectral lines. Are we clear, right? So the point is, it's not from n equal to 1, it is from n equal to 2. I will tell you how in just a few minutes, okay? But this idea that the transition is happening from n equal to 2, that gives us a measure of the temperature of the source where from, these lines emanate. All right. Now this particular series, starting from n equal to 2, is what is called as the Balmer series. Now you must have all studied about the Lyman lines, the Balmer series, etc. in your 11th and 12th, right? Now what you study in your 11th and 12th standard has an amazing connection with astronomy and astrochemistry, right? They're all from hydrogen atom, and the prominent lines, okay, right? They are helpful in actually, even assessing the temperature of the source that is emitting. So this was a qualitative statement, right? That, okay, these lines are helpful in getting us the temperature, but how? Let us take a look at an example, okay? And say, for example, okay, now for the sun, right? The N2 by N1, that is, let's say, the number of molecules present in, let's say, for the sun, if we study H atom spectra, okay, right, we get the information that the N population, right? By P, right? I'm using the word population. I'll explain what this is soon, okay, right? NP from N equals to, that is, the Balmer line, right? Vis-a-vis NP from N equal to 1 level. In other words, we are talking about the lines obtained, the hydrogen atom spectral lines obtained, right? As N equal to 2 being the starting point, versus N equal to 1 being the starting point. Now, NP refers to, right? NP refers to the population of the N equals 2 level. Okay, right? So, and then NP here refers to the population of the N equals to 1 level, right? So, I'm just going to use shorthand notation as NP2, right, by NP1. Are we good, right? So, this is going to be the shorthand notation. Now, this ratio, right? This ratio can be obtained from experiments, right? From experiment. How do you obtain this ratio from experiments? Well, you don't get the number itself directly. The only information you get is the intensity of the lines, right? So you measure the intensity of the lines. So by measuring the intensities of the lines, of the spectral lines, we are okay, right? So by measuring the intensities of the line, you get this ratio. Okay. Now this was found to be, let's say for the sun, this was found to be something like 5.15 into 10 to the power minus 9. Of course, this is just a number. It has no dimensions because it's a number here and number here, so they get cancelled out. Okay, right? Now understand the meaning of this number. I mean, there is going to be some emission from the N equals 2 level also, right? So the N equals 2 level is also going to undergo a lot of transitions, which is going to give rise to these lines. But the key fact to note is this ratio is 10 to the power minus 9. So from the sun, right? So from the sun, predominantly the emission takes place from the N equal to 1 level, right? But nonetheless, this ratio is going to be very important for us to determine the temperature of sun. Let us see how. Okay, I'm going to call this page number 11. Okay, so given this ratio, right? Yeah, we can find out the temperature of the sun. When I say the temperature, I'm talking about the surface temperature. Okay, right? Let us see how. What do you think we're going to do? Well, recall from our previous tutorial, right? We're going to first assume LTE. Right? We're going to assume LTE, right? In other words, that I can even define one particular temperature value for the sun surface. Okay. Then we know that, right? We know that from the Boltzmann distribution, right? My N2 by N1, right? That is given by 5 point. I mean, this is the calculated one, experimentally obtained one for this, but this is given by G2 by G1 times e to the power minus beta times delta E, where my delta E is E2 minus E1, because there's a negative sign already there. I started this lecture with this correction, right? So using this, and beta is 1 over kBT. So using this relationship, we can actually estimate the temperature of the sun, right? If we know this delta E quantity. So in the next lecture, what we shall do is, we shall actually be applying this equation, right? And we shall see how we get the temperature of the sun from getting to know this ratio experimentally. All right. So I stop this lecture at this stage, noting that in this lecture, I basically started with the correction and clarification from the previous tutorial and a lecture, say, which was probably lecture 43 or something like that, right? And then I summarized where we are in this course, and I started off with the hydrogen atom spectrum. And I told you that the Balmer line, that is, the lines which are emitted from the N equals 2, and by computing the ratio of the intensities of the line, right, obtained from the N equal to 2 series and N equal to 1 series, we are going to be getting a lot of information about the temperature of the the interstellar source that is emitting the light. We shall see how this is done in the next class. Thank you so much.